first action to do is to connect to the Moodle in the data analysis tab, and you will find a group choice, programmer or non-programmer, and you should select programmer. After this selection, you will be able to see the track B programmers. And in this track, there is the Python requirements that you received already by email, the video of the installation of this requirement. But the important part is this other new file, a zip file called data and notebooks. Okay, please download this zip file and unzip in the same directory where are the others. So for instance, in my case, I have this directory in the desktop, course FINDHR. I downloaded the zip file, which is DA programmers.zip, and unzipped. This will add in the data folder additional dataset, additional to Titanic that we saw already, and in the notebooks, additional notebooks in addition to 00 sample notebook. Okay. Before starting looking at these files, these notebooks, what is the program for today and tomorrow? But let's look at the program for today. If we go in about this module on track B programmers, we have the agenda for today and tomorrow. DA01 Python is today, and DA02 Python is tomorrow. So today we have a welcome introduction. I will show you using some slides the overall picture, and then we will look one by one in the various notebooks. We will start with the data preprocessing, then a short break, and in the ranking model. After the coffee break, we will look at the fairness part of the ranking. In each of the notebook, there will be a short introduction tutorial of the content of the notebook. Then we will split into groups by using breakout rooms feature of Teams, or people in presence will be just here to do some practice. We will not do practice for the data preprocessing because it would take too much. You know that data preprocessing is typically very time consuming. Okay, if you have any question, please ask at any time. Do not use the chat to ask questions because I do not see the chat. Just interrupt me. Okay? Any questions so far? Okay, let me start with a few slides. This is an hands-on session, so we will not introduce new theory, just recall something. But it is important to have a picture of what we will do in these 2 days. So the objective of the data analysis module is to practice with some data and notebooks in the typical process involved in training a ranking model and explaining the ranking model, and also in correcting the model for what concern the fairness or the unfairness of the module. Overall, we are split into 4 groups. 2 groups will be with for non-programmers, and they will use a visual tool called K9. At some moment tomorrow, we will group all together, and you also see something of this tool. But don't worry, it is just a visual representation of the steps that we do also in Python. Instead, our 2 groups are we will use Python notebooks. The 2 groups are the group in presence and the group online. Okay, and these will be common today in the various notebooks, various parts, and in the beginning of tomorrow. In the second part of tomorrow, programmers and non-programmers will be matched together, the online or in presence all together, to exchange also different views between the more technical part and the less technical. Typically, non-programmers are person which are from HR resources or have not a technical background. And so they may have a different technical point of view. One important aspect that we have to stress and to be clear since the beginning, we will use some synthetic datasets. These datasets are fixtures. This means they are generated for practicing, but they are not data which is intended to be representative of a real life situation. So we cannot make real inferences from these exercises. These datasets are not even generated synthetically, but starting from real curriculum or real job offer. So there is no ground truth behind this data. So we will do exercise, but the dataset has been constructed purposely to show unfairness, for instance, but we cannot conclude if in our dataset, for instance, there is a certain discrimination against women. We cannot conclude anything about the real situation in Europe, in Italy, or whatsoever. Okay, the data consists of 200 job offers. For each job offer, there are between 25 and 150 applicants, curriculum. And 80% of the curriculum are consistent with the job offer, and 20% is almost random. Okay, this is important. So our purpose is to practice with the technological part, not to make inference on what we obtain as results. Okay, what we will see. Let's start from the typical pipeline for the screening process. We have in the beginning data about job offers and candidates. And for candidates, we have feature extracted from the curriculum. From job offer, we have feature extracted from the job offer. So for instance, the job offer may require certain skill or certain language spoken or certain age. And the candidate may or may not satisfy these requirements or may satisfy partially. So the first step is a pre-processing step, which for each candidate to a job offer, compute some matching function. How much each feature required by the job offer is satisfied by each candidate. So this matching can be just 0-1. Either the candidate knows English or does not know, or can be a percentage. If the candidate is required to know 3 languages and only 2 are known by the candidate, we have 67% of the matching. From this pre-processing, it is computed in output a so-called fitness metric. Let's see an example of, let me go a little bit forward. A fitness metric matrix, basically for each feature, like the type of contract of the job offer, the education, the experience, etc. We will see this feature in the notebooks in a moment. For each pair of job offer and candidate, in the matrix, there is the result of the matching. Please notice that we will use the job offer ID. We will call the job offer ID the QID, and the candidate ID the KID. This is strange to use Q and K. It is from, let's say, historical reasons in this area, because there is a parallel of this problem in retrieving documents like in search engine. And so Q stands for query, the query that you search, and K for the document. But let's go back. So the first notebook that we will see is this pre-processing notebook. And the non-programmers have an equivalent notebook, which is called workflow in K9. So they will see the same steps, but with a different tool. After the fitness matrix is computed, this will be the input to train a machine learning model. And the model will return on new data, new pair of candidate and job offer, a score of how good is the matching of the score of the candidate with the job offer. And typically, based on this score, the top K candidates are selected for interview, for instance. So they are ranked up to a certain number, which is the number of person invited for the interview. we will deal with this part of the process in the ranking notebook. Next, there is this new requirement for AI models to provide an explanation of why a candidate received a certain score. We will deal with this part in the explainability notebook tomorrow. The other point that will sorry, let me go a little bit. The other point that we will consider is what happens if our model is unfair. That is to say, give an advantage to certain social groups and disadvantage to other ones. We will study in the FAIR ranking one possible approach to make the model less unfair, which consists of changing the fitness matrix from the one computed to a new version, a fair fitness matrix, in which historical correlation between protected groups and good score and bad scores are removed. Okay, so this is a so-called pre-processing FAIR approach, and by adding this before the construction of the machine learning model, we let the training algorithm not to discover patterns which disadvantage the protected group. And we will see this part later this afternoon. So let me go back. So the first part is the pre-processing. I will now start the first notebook, and the purpose of this notebook is twofold. First, we will look at our files, our data source, in order to get confident with the features that we will consider. Of course, these features are not the only one possible. There will be more rich data set in real systems. And the second part, the second objective is to look at how to implement these matching functions. So how to start? Basically, I will start with a shell Anaconda. We'll move to the directory where I downloaded the zip files. So in this directory, there is everything that we downloaded, including the recent data and notebooks. Then I need to activate the environment created during the installation of the requirements. So Conda activate course FINDHR. Okay, so in this environment we have installed the various requirements, and so everything should work. Next, we just start the Jupyter Notebook program. So this is a common step for programmers, but I don't know how much you are expert or used with these Python settings. Okay, let me start. Jupyter will open a browser within the directory where we are. Okay, and so under data, we have the various data, and under notebooks, the notebooks. Just a mention on what is in data. We have here actually not only the input file, but also the file produced by the various notebooks. So this means if you have a problem with one notebook, don't worry, because you can run the other notebook without problems, because all the input to every notebook is already available. Okay. Okay, we start with data preprocessing, and according to the program, we will have, we are in time, about 30 minutes to look at this. Let me say again, since data preprocessing is very time consuming, we do not have time to do exercises on this. Okay, so the notebook starts with an introduction describing what is the content, the objective of this. There are input dataset in tabular form. We have 3 input. The candidate data source are basically is basically the file with the curricula features about candidates. The job data source are the features about the jobs offer. There is a third input called here application data source, including for each pair of candidate and job offer application, the score. So we do not mean that every candidate in the candidate data source is applied to every job offer. In this other file, there are only the pairs of candidate applying to the job offer. For simplification purpose, actually, if you want to check, each applicant is applied only to one job offer. So there are not applicants repeated. What is in the application data source? There is which applicant applied to which job offer and the score of the applicant. The idea is that this score is given by historical data. We take past applications and we record, we assume to know in past application each applicant how much scored for that job offer. Scored by who? By the screener, typically the human screener. So we have an historical data set of person applying to job offers. They were evaluated by HR, which gave a score. Machine learning learn from the past. So when we will see the machine learning model, the idea is to be able, the model, to understand what is the logics, the pattern assigning score two candidates. Actually, in this file, if we look at the data, so we have the curriculum are the candidates, the job offer, the job offers, and score is the include for each candidate and job offer the score received. Each of these files has two versions, version 1 and version 2. Version 1 is for me to make the presentation and for you to also make exercise, and version 2 is if you want to do further exercise. So the data is slightly different in the two cases. For the score, there are actually 4 versions, not only version 1 and version 2, but a version called fair and a version called unfair. So these are historical data. In the fair version, the score was assigned with a fair logic. In the unfair, in score unfair, the score was assigned by privileging men against women or non-binary. Okay, but we will see these later. Okay, how to load this file? These are CSV, comma separated values. And so we will use standard libraries like pandas and NumPy, but we will also use the specialized package called FINDHR, which you installed during the requirements to perform some specific preprocessing step. So first, we import the libraries. You can repeat the step with me. Everything should work if requirements were correctly installed. Then we set the path and parameters. So the directory with the data is in the data folder, and the suffix for which of the two versions to use is in this variable. And then there is the name for the curricula, the name for the job offer, and the name of the file for the pairs of applicant to job offer in two versions, the fair and the unfair. Another parameter which is important is top K. How many applicants for each job offer we want to select, to invite to the interview, for instance. This will be used later. Okay, the first step, let's load the data. Before loading the data, let me have a look at the content of the curricula. So we have the curricula ID and the various features. One less known capability of pandas is that in a column of the pandas data frame, we can have not only scalars, for instance, the numbers 0 or the string 3D printing technicians, but in a column we can have also more complex data, let me go in the back, it's more simple. For instance, look at this column value. It is a string, but it is a string that represents an array of strings. Okay? For instance, the languages spoken by this applicant. So this capability, the capability of pandas is that in a pandas data frame, in a column of a pandas data frame, we can have not only scalars, numbers, strings, but also more complex objects, for instance, arrays. Okay? This is not very well known, but it's very powerful. So why this? When loading a CSV, we can transform the string that we have seen with in its inside the array into an actual array. How? By this function here, convert, which tests if the content of a value is an integer, a float, or a list, we just return that value. Otherwise, we interpret the string, otherwise is a string. We interpret the string trying to decode the complex type. This literal eval does the job. Okay. So in the read CSV, starting from the file of the job offer or the file of the curricula, we read the scalar column without problems. But for the columns which contains complex objects, arrays, we apply this conversion. Okay. So we read the job offer, the candidate, and the file with the score. Let's look at each of these three data frames. Now they have been read from CSV to Pandas data frame. The first one is the job offer, JDS. It contains a number of columns. Let's see one by one. QID is the job offer ID. It's just a progressive number. Then occupation is the standard title of the job. This is standard. The name of the jobs have been taken from the ESCO taxonomy, which is a European categorization of concepts related to jobs. Notice that the name of the column have a suffix _J, because also applicants will have similar features. So to distinguish features of the job offer, the required features from features of applicants, we will use _J for the job offer and _C for the candidates. But let's continue. So we have the occupation is the job title. Education is the minimum education required for the position. And it can be one of these possible values. So starting from right, a PhD, a master, a bachelor, a degree. Any is a spatial value, which means any level of education is okay. So the idea is the job offer require the candidate to have a minimum degree, or any means any degree. Gender is the gender required for the position. Again, any means any gender. Actually, in let's say for most of the job, it is illegal to require a specific gender. In some cases, it is legal if you have to hire an actor for a male person, must be a male. However, if you are curious, if you go through the column, there will be any in all positions. So this data set actually of job offers does not have discriminatory requirements. Age is the minimal a pair with the minimal maximal age required for the job position. Contract is the type of contract offered. Can be in presence, hybrid, remotely, or any, which means any type of contract. Nationality is the required nationality. Competences is a list of required skills, again by using the ESCO taxonomy. And knowledge is again a list of expected knowledge by candidates. Languages are the list of languages required to be known by candidates, and experience, the number of years of experience in the position. So in the first case, it is required to speak Italian and French and to have at least 1 year of experience. Okay, so we have here a few lines with 5 job offers. In general, in our data, we have 200 of these job offers. Let's look now to the candidate. In the CDS, we have 1 row for every candidate. The first column is KID, the candidate ID. And then we have similar columns like before, with the feature now possessed by the candidate. So the occupation is the current occupation. The education is the education level. Now it's not the education required, but the possessed. The age, the gender, the type of contract that the candidate would like to have, the nationality, the list of competencies of the candidate and knowledges of the candidate, the language spoken, and the experience of the candidate. Okay? We have okay. We have altogether 17,000 candidates applying to the 200 job offer. Let's look at the third file, which is the file which store which candidate applied to which job offer and what was the score of this application in the past. So in this case, it is the fair one. And so candidate 0 applied to job offer 0 and received 0.48 of score. The score has been normalized in a number between 0 and 1. Okay, so you can think of how the percentage of that the candidate satisfy the requirements or was judged to be appropriate for the position. Okay, this is the first part of this notebook. So we have still some time. The second objective of this notebook is, after having get confidence with the data, to look at how the preprocessing can be implemented. Recall, the preprocessing means building this fitness matrix here by using matching function between the job offer required feature and the candidate possessed features. How to implement this part? We could use scikit-learn standard feature processing. In the FINDHR, we propose something in line with the pipelines, but a little bit more specific and refined. The first thing is enriching the standard metadata of data frame. A metadata is a property of a column, typically the type of the column.
Sorry, Salvatore. There is
Yes.
a hand up in the Teams. They raised their hand.
Please, since I do not see the chat, just interrupt me and ask by voice, please.
Hi, I am Sharathi. I'm the one that raised the hand. So just before getting to the metadata, we had the FAIR. We saw the head of the data frame of FAIR matchings, if I'm right. Who determines if it is fair? Like, is it human done by humans,
Okay.
algorithm?
Yeah. It's called FAIR because this data has been generated synthetically to be fair. In the unfair version, the unfair data has been generated to penalize certain groups. So who decide it is fair? In our exercise, it is by construction because it is synthetic data. In real life, we do not know if our data, our historical data is fair or is not fair.
Okay.
When we deal with fairness, we will measure how fair is the historical data and how to mitigate the unfairness. Only because the data is synthetically generated, we can say that the input is fair or is unfair. But in general, your objection is correct. We cannot know a priori.
Okay, thank you.
Thank you. So once again, please stop me by voice. I do not see the chat. So what kind of metadata we have? We have proposed an extension which resort to this JSON schema standard. JSON schema allow to specify the structure of some data, and this is useful to double check that the input in the CSV has a certain structure. How it is specified? For each input file, we specify a dictionary mapping every column to this object, JSON metadata, in which we pass the expected schema of the column. So we expect, for instance, the QID, the ID of the job offer, of type number. Or the occupation is of type string. The power of the JSON schema is that we can specify more complex structure. For instance, education is of type enumerated, and so only these possible values can appear in the education column. Or age, recall it was a pair, the minimum and maximum, and so we can specify that it is an array of 2 items, a number, which is the minimum, and another number, which is the maximum. The gender is enumerated, contains male, female, non-binary, or any. So what is the benefit of using this? For our, let's say, simple example, it's not that important. But if you think of an industrial context in which data is collected from various sources, it is important to check that the input data has the correct structure before processing the data. So in every column, we have only certain expected value. So it is a matter typical in data collection and processing in ETL, extract, transform, and load. So here we specify the type for the job offer, the type for the candidates. For instance, in the candidate gender, there is only male, female, non-binary. There is not any, because recall any means any gender expected in the job offer. So once we specify what we expect in the input data frame, we can validate the data frame read from CSV against the expected structure. Okay? So this validation is offered by the validate schema method, which goes through every entry in the dictionary. So for instance, KID, the entry expect type integer, and for each value in the column of KID of this data frame, check that the value is actually of this structure. So this part is not for the moment strictly something strictly necessary, but it's good to have in order to avoid our model to learn an unforeseen value or strange incorrect value loaded. Okay, then we join the metadata of candidate and job offer, and we set a few lists with the ID column name, so the job offer and the candidate, the predictive columns, the columns that will be used to build the fitness matrix, columns not used, for instance, the occupation is not used, just to make an example of something not used, One important column is the sensitive one, which is the column describing the groups for which we do not want to discriminate. So we do not want the model to be unfair against the gender. This is important to have in order to check if there is unfairness in the score against this group. And finally, the target column is the column, the value to be predicted. Score is an historical value. Machine learning model learn from historical data to predict a certain target value, in this case, the score assigned to candidates. What is the benefit? That if the model is perfect, it will be able to reproduce the score of human resource personnel without the interview. This is the benefit of having machine learning model to replace person. Okay, to replace person with engineer that train the model. Okay, let's see how to compute the fitness matrix. First of all, we join our three dataset. So this is done with the merge method in Pandas, which takes two data frame and the join condition. And so we join all three of them. And what we get is this table here. In this table, we have everything for every job offer and for every candidate which applied to that job offer, because we join also with with the ADS, the data set containing all the applicant to a job position. So for each job position and applicant applying to that job position, we have the feature of the applicant, underscore C are for the applicant, the features required by the job offer, underscore J are the features of the job offer, and the score historically assigned to that candidate in when the candidate applied to that job offer. So this is the big join of with all the feature all together. No, because we start from the file in which we have all the pairs of who applied to what. And for instance, to job offer 0, we have a candidate 0, 1, 2, 3. But if we go to job offer 1, we do not have any more of those candidates. Actually, in our data, every candidate applied to only one job offer, which is a special case. In general, a candidate may have applied to more than one job offer.
So one job offer?
Yes.
One candidate, just one.
Yes, exactly. So how to compute, let me recall what is the output of the preprocessing. Is to compute the fitness matrix, how much a candidate satisfies the requirements of the job offer. So let me go first to the output and then how to reach. The output is something like this, in which, again, we have the job offer, the candidate, and how much the candidate contract match the job offer contract, the candidate gender match the job offer gender, etc. Let's see how to compute this. Basically, we could use pipelines, the Schickeler pipelines, but since these matching functions are quite typical, in the FINDHR APIs, we offer specialized pipelines which implement this matching and also take advantage of the metadata. So in order to specify the matching, we define this dictionary in which every entry of a dictionary is mapped to a matching function which is predefined in FINDHR. What is the meaning of the key? The meaning of the key is a pair. The first element of the pair are the column to be matched. The second element is the name of the column in output. So we take the contract of the job offer, the contract of the candidate, and we apply the match binary function to compute fitness contract. What is this match binary? It is a function which returns 1 when the value for the job is equal to the value of the candidate, or the value of the job offer is any, or the value of the candidate is any. So for instance, if the job offer contract offered is remote and the candidate contract wanted is remote, there is a matching of 1. If instead the contract of the candidate is in person, there will be a 0 because they are different. However, if the job offer contract is any, whatever the candidate wants, there is a match because any contract is okay for the company. Or if the candidate contract is any, the candidate want any remote or in presence contract, there will be also a match. Okay? Binary means that the output will be 1 or 0. The same for gender or for nationality. Either the candidate feature match or not. For other feature, this matching can be not just equality, but greater or equal. For instance, in the education, if the job offer require a master degree and the candidate has a PhD, that's fine. Okay? So the match is when the job offer value is greater or equal to the candidate value, or the job offer is any. Another type of matching is inclusion, which is 1 when the candidate value is included in the job, in the range of the job value. Recall, age in the job was a pair, the minimum and maximum age. And so we test if the candidate age is in between the two bounds of the job offer age. And finally, match feature set return the fraction. Actually, there is no one here. So return the fraction of the job requirements that are possessed by the candidate. Think about the language. Language J is the list or the set of languages required by the job offer. Languages C are the languages spoken by the candidate. We take the fraction, how many languages expected are spoken by the candidate over the total number of languages expected. Okay? And so this will not return 0, 1, will return a number between 0 and 1, the fraction of languages required that are spoken, or the fraction of competences required that are possessed by the candidate. Okay, by specifying this long list of matching functions, we can build a pipeline which now is not implemented using standard scikit-learn step, but it is implemented by FINDHR API, in which there is a preliminary step that inject in the pipeline the metadata. Then this derived column which implement the matching we have specified before, and a final step which detach the metadata. Why we have this metadata? They are, let me repeat, they are not strictly necessary. It is a new feature offered by the FINDHR API in order to facilitate the implementation of this function. And also we will go back tomorrow when we will speak about explainability. Through the metadata, we can better reason on what happens during these transformations. In the end, we get a pipeline like okay, probably I missed or I changed something in the FINDHR here. Let me run from the beginning. Okay, what does this pipeline return? Like any pipeline, there is a fit and transform. Fit is used to over a data set to construct all the intermediate data structure needed in the pipeline, and transform to apply the transformation to the dataset. And so the usage, in the end, we get, if you look, we get a pipeline, exactly a standard pipeline. After fitting and transforming, we get a big data frame in which, in addition to all the feature of the candidate and the feature of the job offer, there are also these new columns: fitness contract, fitness gender, fitness nationality. So all the matching function return a new column which is added to the data frame. In the meantime, it is working. Okay, this take time, the validation. However, in our fitness matrix, we do not need anymore the original feature of the job offer and the candidate. So we remove by keeping only the ID columns, QID and KID, and the column that start with fitness. Okay? And the sensitive column, the gender, and the score. Okay? The fitness matrix is used together with the score to train the ranking model. The gender column will be used to check for fairness. So after building this matrix, we do the same for the unfair version, for the dataset with the score which are unfair, and save the fitness matrix with the name fitness mat, the suffix, and then fair or unfair. Okay. Okay, this close the data preprocessing. Let me recall for people that in the data folder we have already this fitness matrix available. And we have two versions, version 1 and version 2. I'm presenting version 1. Version 2 is our data set slightly different, the same columns, but different applicants to the positions. And so in the fitness matrix, in the end, we will have this big matrix with for every job offer and candidate applying to that job offer, the value of fitness for each of the feature required by the job offer. And in the end, the gender and the score, the historical score assigned to that applicant for that job offer. So the plan for the next 50 minutes is to introduce you the second notebook about ranking. We start going a little bit faster. In this notebook, we load the fitness matrix saved in the first notebook, and then we follow the typical process in machine learning, at least in the development of a machine learning model, which consists of splitting the data into training and test. These are two data sets. One is used to train the model from historical data. And once the model is trained, it can be applied to new data. In order to test the quality of the predictions of the model on new data, we used the test data, in which we do not only have the feature to make the prediction, but also the historical score in order to compare how close is the predicted score with the historical one. Okay, so we train a ranking model on the training set and make prediction on the test set. What kind of evaluation on the test set we can do? There are two metrics to evaluate. One is how good is the prediction, how close is the prediction to the ground truth historical score. This is called accuracy, but we will use another metric, not just accuracy. And the other is how fair are the predictions. how to evaluate this. First of all, the algorithm to train the ranking system will be LambdaMart, which is an algorithm which try to understand under which condition certain feature are have a better score than others in the historical data. It is let's say a model which behind the scene build other models. These other models can be very large, and it is the number of these other models is in the n estimators parameter, by default 100. Basically, it's called an ensemble model in which every of these 100 models try to improve the previous one when the previous one was incorrect. And in doing this improvement, the learning rate is control how much improvement we want to manage. The smaller means the more search for better model is done. If we are okay with a larger value, the search algorithm stop earlier. Regarding accuracy of the predicted model, we will not use just accuracy, but we will use, let's say, the correlation between the ranking produced by the model, fixed job offer, the model assign a score to each candidate, and so there is a natural ranking from this score, and the ranking of the ground truth. What happened for that job offer actually in the past? We have the score given in the data, and so we have the ranking of the candidate also on that score. So the normalized discount cumulative gain compare how the two ranking relate each other, but giving to the top position more weight than the bottom position. This means that if the prediction are okay in the first positions, in the first ranked candidate, this is more important than being wrong in the first position and right in the bottom position. Why? This is natural because the HR will look at the first positions, will interview the first position. And so basically the NDCG is a number which look at the relevance of a candidate I weighted by this other formula 1 over the logarithm of y plus 1, which decrease as y, the position of a candidate is in the bottom. N stand for normalized, which return a number between 0 and 1. Okay, so NDCG equal to 1 means the ranking of the model perfect is perfectly the same of the ranking of historical data. Regarding fairness, we will measure this with the notion of statistical parity, which look at the top K candidate, look at this matrix here, confusion matrix, contingency matrix. We have the two groups, male, not male, and on the rows. And on the columns, how many were in the top 4 or out of the top 4. In this case, we have 2 male and 2 not male in the top 4. Is this a fair situation? Depends how we measure fairness. One way to measure fairness is this statistical parity, require that the fraction of the two groups in the top K is representative of the fraction of the two groups in the applicant pool. So it's okay that we have 2 not male, but in the overall pool of applicants to the position, we had 10 not male, and so the percentage of not male is 2 out of 10, 20%. If we look instead at the percentage of male admitted, is 2 out of 5, 40%. So proportionally, only 20% of the female were admitted, not male, and only 40% and 40% of the male. So the disparity, the statistical disparity metric, is the difference between the fraction of male admitted minus the fraction of female admitted. So in this case, male were admitted 20% more than female. And so we look at these for top K, where K in this case is 4, but can be a parameter. Notice that also the NDCG metric is parametric in K. So actually, we fix a K and we measure how good is the ranking up to K, how fair is the set of top K persons. Okay, so in the second ranking model notebook, we import the libraries, we set the parameters exactly like in the first one. We load the fitness matrix with the features, the gender, and the score. Then we add to the matrix also for each job offer the rank of the candidate. How we can add the rank? We can, for each QID, for each job offer, we use the rank function, which assign the ranking position in ascending order of score. So in descending order, so ascending equal to false. So the highest score is the first, then the second highest score is the second, and so on and so forth. So for instance, here, this is the highest score, and it was ranked 1, the second highest, etc., etc. So we can assign, we can introduce this new column based on rank. Then we select one of the two fitness matrices. We have the fair and the unfair. Let's consider the unfair fitness matrix. Why the unfair? Because we want to discover that the model is learned to be unfair like the historical data. How to split into training and test? We use the typical train test split function of scikit-learn. And so we divide the data set into 20% test set and 80% training. The 80% training is further split by taking 25% of these 80 for determining the hyperparameters, which is a way to optimize the search for the best model, and 75% for model construction. Here, the test size is 0.2, which means 20% for test, 80% for training, the remaining one. One important thing in the training and test is that we cannot randomly split the data into training and test. We should split first based on the job offer. Either all applicants to a job offer stay in the training or stay in the test. We cannot have some applicants in the training and some other in the test. Okay, so the split is done not on the fitness matrix, but on all job offer ID. Okay, so the first line compute the ID of the job offer in our dataset, in our fitness matrix, and these job offer ID are used splitted into 80 and 20%. Moreover, in real situation, what happens? You build the model today, you use the data up to today for training, and you apply the model to the job offer after today. So the split typically is not shuffling randomly, but it is temporally guided. So a way to do temporally guided is by setting the shuffle parameter to false in the train test split. And so what we get is the job ID in the training, in the test, and in the validation. The validation is used for hyperparameter search. Then we build the actual data frame for training by considering of the fitness matrix the rows for which the QID is in the training, in the validation, in the test set. Okay, so basically we first partition the job offers, and then we take all the data of this job offer appearing in training or validation. How to build to train the model? The predictive column that we want to use are these ones. So the fitness of the contract, the nationality, the education, the target was score, and we have created this rank here, which is the column with the rank position. The algorithm lambda rank is implemented by this library. LightGBM is a famous and well-performing algorithm for machine learning. And so basically we create a LightGBM ranker whose objective is the one or lambda rank, and we have as parameter what we have seen in the slides, the number of estimators and the learning rate. Then this algorithm, if you know the typical machine learning algorithm, is fitted over the training set. But when dealing with our ranking data, actually we want this algorithm to take into consideration all the rankings within a same job offer, okay? Because this algorithm has to reproduce the ranking by looking at historical data, job offer by job offer. In order to this algorithm to know which rows in our fitness matrix, which rows belong to the same QID, so what are the applicant to assign QID, and so what is the ranking. In order to pass this information, we count for every QID, for every job offer, how many applicants are in that job offer. So this count here, so for instance, the first job offer is 29 applicants, the second 61, etc., etc. This count allow the algorithm to look at the rankings by considering the 29 applicants. This is the first ranking. The second ranking are the next 61 applicants, etc. So this information is the algorithm internally to be able to reconstruct the various, separate the various ranking. So we call fit by passing our training set, which is the fitness matrix for the predictive column. Then these are the predictive features. The feature to be learned is the ranking. Okay. One small problem with this implementation, it expects the ranking not to be one the top, two the second, etc., but the other way around. So let's say instead of having 1, 2, 3, 4 the order of the rank, we should have 4 the top, 3 the second one, 2 and 1. Okay. And so for this, we change the, we pass from the rank starting from 1 to top K to top K to 1. And so we reverse the numbers. In the search for the best hyperparameter, it requires to pass the evaluation set. Recall we divided 20% for test, 80% was further divided into training and evaluation. And so here we pass the evaluation again with the predictive columns and the ranking reversed. And this algorithm use NDCG metric to guide the choice of the hyperparameter. The NDCG metric is evaluated at top K. So this is a parameter that was set in the first cell here in the second one. So it is 10, fixed to 10 here. Okay, so the fit start from the training set and return a model which can be used to make prediction. Let's use it. Let's consider a job offer ID, the number 160. And this is the first one in the test set. Recall, we have 200 job offer. The test set is the last 20%. So start from 160 to 199. So this is, it consists of 40 applicants, and these are the fitness matrix for these 40 applicants. How to make the prediction? We ask the model, which is in the ranker variable, to make a prediction, and then we pass all the 40 applicants to this job offer. The result of this call is the predicted score, which is called lambda, actually. Given this predicted score lambda, we can apply the same function as before to produce the rank. Now, the lambda, the highest the lambda, the better the rank. Okay? So in output over this data frame, we have the predictive columns, and then including the score of the ground truth, the rank of the ground truth, and the predicted lambda, the predicted score by the model, and the predicted position by the model. Okay? So we can compare now the rank from the historical data built over the score with the predicted rank. How? For instance, we could just plot them. On the x-axis, we have the predicted rank. On the y-axis, we have the ground truth rank. Okay? So if the predicted rank is the same as the ground truth, we should see these applicants to be on the straight line. Okay? So the first 3 applicants were predicted correctly, were exactly the top 3 as in the ground truth. Then there is some mistake around here and here. So basically, how to measure how good is this prediction with the NDCG, which is implemented in the scikit-learn. And so we can compute the NDCG by passing the score, the true score, and the predicted score, and at which position we stop. Recall the NDCG compare the first K. So the result in this case is 0.979, which is very good. And it's good because the top position were correct. And we stop at the 10th position. We can compute this NDCG not only on a single job offer, the 160, but all of them, and plot the distribution of the NDCGs. So this plot here shows which for each value of the NDCG, how many job offer have that value. So most of the job offer have an excellent NDCG, which is close to 1. But also this job offer here has 0.90, which is very, very good. Okay. The other point to evaluate is the fairness. How to evaluate? We compute the contingency matrix with the gender on the rows and whether the person are in the top K or not. This is just counting, but since we will consider binary gender, we define sensitive to be a new colon, which is unprotected if male, else protected. So female and non-binary will be renamed protected. And then we count in the 160 job offer, we have 23 protected, 17 unprotected. How many of them were in the top K? We just restrict to the predictions, to the predicted rank to be at most top K. K was 10. And again, we do the count. So we have 9 protected and 16 unprotected. But why we have 25 here? Top K was 10. Because of ties. If there are ties, they are considered at the same rank. So, what is the fraction of unprotected in the top K? 95%. So we have called 100 the total number of male. It was 17. 16 were in the top K. What happens for the protected? Of the 23 protected, only 9 were in the top K. So the fraction is 39. Okay? The difference between 94 and 39 is the disparity. In this case, 55% almost. Okay? In general, we can give the final function that compute this disparity and call just disparity over the predictions. Then we can compute the disparity for every job offer in the test job and compute the mean of this disparity. So on average, a job offer in the test set has a difference of 18% in the percentage of male minus female. Alternatively, we can compute the job offer over all the test set, the disparity over all the test set. What does it mean? Take over the test set all admitted male, all admitted not male, and compute the fraction of admitted over the total male, the fraction of admitted not male over the total not male. So computing the disparity over all the test set means globally in the test set 25% male were admitted, 25% more than female in any offer, not just in a single offer like 160 and not on average. Okay, this is the typical process. What should we do now, or we continue? We start now, then we continue after the break. We should do this exercise here, in which you try to rerun the notebook and observe the matrix of NDCG and disparity at the variation of the group of dataset, suffix 1 and 2, the top K, so far we considered top K equal to 10, and the parameters of the algorithm landmarks, which are in the previous slide. How it works, what I would like to present before continuing with the exercise is the step in which we transform the fitness metrics in input to the machine learning model by making it fair. What does it mean? Removing from the fitness metrics any correlation with a protected attribute. How to remove that? There are several algorithms. We will use this LFR, which stands for Learning Fair Representation. So it takes, it is fitted on a training set, and it can transform both training and test to remove the correlation at the top K rankings. Correlation with a protected attribute that we must give in input. This protected attribute may be not used for predictions for ranking, but it is needed for correcting the data in order to calculate correlations. This algorithm has itself a number of parameters. K is the same K used so far. And then there is this AZ, which by default is 0.5. It is the weight of the fair correction in the loss of the algorithm. Intuitively, the higher this number, the more correlation is removed. And so there is in the processed fitness matrix less and less correlation between the other predictive attributes and the protected one. These other parameters restrict to candidates with a minimum threshold, but basically putting 0.0 means applying to everybody. How it is implemented? If you open the third notebook, fair ranking, you will find just one cell. This cell has to be copied inside the notebook that you have looked at so far at a specific point here, where is the forward pointer. What is this pointer? This is the point before training the model. At this point, what does the cell? The cell uses an implementation of LFR, which takes a binary protected attribute. In this case, we transform gender to be binary, male unprotected, all the others protected. And then create an object, learning fair representation, at which we say what is the job offer ID, and so which are the different applicants, the applicants to each different job offer. What is the sensitive attribute, which is this binarized here. What is the ground truth, the score, which help in determining the ranking within the job offer ID, and what are the predictive column to be transformed, the parameter top K, and the parameter AZ. Actually, the loss has also other parameter, but we keep the other parameter fixed. We can change this AZ to give more importance to fairness in the preprocessing. And this is the object. It is fitted on the training set, and it is applied with the transformation to the training set, validation test set, and test set. This transformation return columns from the predicted columns renamed with _fair and added to the dataset transformed. So we will have the dataset that we are transforming, the train dataset over the predicted columns, and as a result, we add to this dataset the transformed column whose name has suffix _fair. Okay. After that, we just set the predicted columns to be the transformed one. So from this point on, everything remains the same, but the fitting of the model, the prediction of the model will be not on the fitness matrix original column, but on the transformed with _fair. Okay. So I will not run this. You will run in the next exercise. So basically, the exercise consists of cut and paste this cell into the notebook you're already working on, and then change the parameters top K, AZ, and see how these impact NDCG and the disparity. These both by also possibly changing the suffix of the datasets to be considered. Okay, so I will now restart the breakout rooms. The exercise is similar to the previous one, but with this additional cell which sanitize the fitness matrix before training the ranking model. Questions? Okay, we have half an hour for this exercise, so we will be back 10 to 20 for final comments of today. So what we did in the ranking model notebook, we executed the typical process for training a model with some, let's say, specific steps considering that ranking is within ranking of candidates within a same job offer. And we found that over all job offer in the test set, an average NDCG very high, 0.99, and a standard deviation of 0.02. Okay. If we look at the fairness, overall, we found 0.18 on average of disparity and a variance of 0.23. If we look at the disparity, not every single job offer, but overall in the test set, it is 25%. So this means that in the overall test set, in all the application on the selections of the test set, men were in the top K with 25% more than women. Now, the other possibility is to preprocess the fitness matrix in order to decorrelate the predictive attributes from the sensitive attribute. Here, sensitive is unprotected for male, protected for female, and non-binary. What does it mean, decorrelate? It means if some attribute in the fitness metric is correlated with this sensitive attribute, the data is perturbed somehow to remove this correlation. We don't know a priori which other attribute is correlated, but it is typically the case that, for instance, let's say minority groups have, let's say, less education or less experience. The result of this data preprocessing is a new training set, validation set, and test set, where the predictive feature have been replaced with a fair version. Now, the point is, once we preprocess the data, change the data, and repeat the training and the test, what does change? Let's look at accuracy. If we now look at the average NDCG, it is 0.9927 that compared to the previous one. Let me enlarge here, which compared to the previous one is almost the same. There is no much difference. The standard deviation is slightly smaller, but basically for this data, maybe not in general, but for this data, the preprocessing has not changed the accuracy of. But the preprocessing was intended to change the fairness. So let's look what happens at the disparity. Recall, without fair preprocessing, disparity was on average 18% and overall 25%. After fairness correction, it is lower, on average 15.5% and overall 21%. So the correction was effective without losing accuracy. In general, this is not always true. We may lose accuracy, but because there is a trade-off. This was done with the default weight for the fairness correction. If we change this, let's say, to a large value, the data, the fairness data preprocessing is instructed to correct much more correlation, to decorrelate much more. So in principle, we expect a smaller disparity and likely a worse accuracy. Also, while it is computing, notice that the learning fair representation algorithm takes in input top K, because this algorithm optimizes NDCG fairness at NDCG-K. So this top K should be the same like in the ranking training, because both should optimize the same subset of selection. There are others parameters, but for the moment, let's see what happens with AZ equal to 10. Let's see for the accuracy is again unchanged, 0.992, because let's say this data set is easy to be predicted. If we look at the disparity, on average it is 15.3%, and overall this did not lower it too much. So let's say, at least in this case, this is the best possible, because even increasing the weight of the correction, this algorithm is not able to, at least with this setting, is not able to improve a lot, much more. Notice that we applied all these on the unfair. We started with the unfair fitness matrix. It means that the score was actually synthetically generated to penalize the protected attribute, the sensitive one. If we try starting with the fair in a situation where historically there was no discrimination against the sensitive, the protected group, then the preprocessing data may not have an effect, because there is nothing to decorrelate, but still the ranking algorithm may introduce new form of unfairness by, for instance, pretending to generalize spurious correlations in the data. What we will see tomorrow is the last step of the process. Tomorrow morning, in the beginning, we will see how to explain the score assigned, predicted for a candidate in given the features, predictive features. So we will study what is the importance for a single prediction of every feature in the fitness matrix, and also globally, on average, what are the features in the fitness matrix that are more important. This is a relevant problem in its own, because the HR wants to know why a candidate has been scored in a certain way, but is also useful to understand globally what are the inferred importance of feature for certain job position. Is the contract relevant, the education, what is historically determining the model to make a certain score prediction.